Welcome to Brain Vision.
So here we want the total rotational kinetic energy of the Earth's rotation about its own axis. So this would be 1/2 times the moment of inertia. We're going to treat Earth as a sphere. And then we're going to say times the angular velocity daily, because again, this will be about its own axis squared. And so this will be equal to 1/2. The moment of inertia is 2/5 mr squared multiplied by omega squared. So let's solve. So the total rotational kinetic energy of the Earth about its own axis would be 1/5 times the mass of the Earth, so 6.0 times 10 to the 24th kilograms, multiplied by the radius of the Earth, 6.4 times 10 to the 6th meters, quantity squared, and then multiplied by the angular velocity of the Earth for about its own axis. So we have 1 revolution, 2 pi radians for every 1 day. And then we're going to multiply this by 1 day. And there are 86,400 seconds per day. And we are squaring this entire term. Therefore, the rotational kinetic energy would be equal to 2.6 times 10 to the 29th joules. And again, this would be Earth about its own axis. Part B is asking us for the total rotational kinetic energy for its yearly revolution about the sun. Now here, we're going to treat the Earth as a point mass. So we can say that here, the total kinetic energy, the total rotational kinetic energy for the Earth's rotation about the sun would be equal to, again, 1/2 times the moment of inertia times the angular velocity yearly squared. Here, the moment of inertia would simply be equal to mr squared, where m would be the mass of the Earth, but r would be the distance from the center of the Earth to the center of the sun, times, again, omega squared. So we can solve. This would be equal to 1/2 times the mass of the Earth, so 6.0 times 10 to the 24th kilograms, multiplied by r squared. So the distance between the center of the sun and the center of the Earth would be 1.5 times 10 to the 11th meters, quantity squared. And then this would be multiplied by 2 pi radians for every 365 days. And then again, multiplied by 1 day for every 86,400 seconds. And this entire term will be squared. And we find that the total rotational kinetic energy for the yearly orbit around the sun would be 2.7 times 10 to the 33rd joules. So this would be our answer for part B. The total kinetic energy would be equal to 2.7 times 10 to the 33rd plus 2.6 times 10 to the 29th. This is equaling, again, if we had to round, 2.7 times 10 to the 33rd joules. Essentially, the total rotational kinetic energy of the Earth about its own axis is negligible compared to the rotational kinetic energy of the Earth about the sun. We can say that the kinetic energy due to the daily motion is about 10,000 times smaller than the total kinetic energy due to the yearly rotation about the sun. That is the end of the solution. Thank you for watching.